So, as you may know, the Fourier series allows a periodic function xt to be decomposed into an infinite sum of sinusoids given by the Fourier synthesis summation. The key to this equation is to sum over each of the harmonics, that is, multiples of the fundamental period omega naught, over all the indices k. Now, on the other end, you might have the signal xt and you want to find the coefficients a sub k, which determine the contributing terms over each harmonic. This is given by the Fourier analysis integral, a sub k equals 1 over t naught integral, and so on. This is not so new. I would now, considering this, I would like to consider the example that we just did in class a couple days ago, given by xt equals 5 plus 8 cosine of pi over 6t plus 4 cosine of pi over 8t plus pi over 3. The arrangement of the classwork to find the Fourier coefficients was to find the fundamental frequency, rewrite the equation as a sum of complex exponentials, then use the inverse Euler's equations to find the Fourier coefficients. I want to note that this is a very cheap or efficient way of calculating the Fourier coefficients that really only arises in the case of sinusoids. You might have realized that even though we know about the Fourier analysis integral, that we never actually wrote it like this in class. And we're exploiting a good property of sinusoids that allows us to calculate the Fourier coefficient very easily. If you were to do the Fourier analysis integral by brute force, for example, you would need to calculate this integral over every single possible k, and you would, in fact, reach the same answer where a naught equals 5, a3 equals 2e to the j pi over 3, and so on. Aside from sinusoids, you should know that computing for the Fourier series or its coefficients comes down to really computational calculus skills or coding it in MATLAB to do it for you, but it's only easy in that sense for sinusoids. In the future, I'll be making more videos on non-sinusoidal functions and generating its Fourier series.